Welcome to the abstract algebra lesson on fields. I'm going to give some definitions, some basic concepts, and then I'll provide a few examples, actually two examples of the construction of non-prime finite fields. We'll see what that means later in the lecture. A field is a commutative ring such that the additive identity doesn't equal the multiplicative identity. In other words, let me point to it here. 1 doesn't equal 0, and all non-zero elements are invertible under multiplication. We have this prose definition from Wikipedia, followed by a more precise definition here. Formally, a field is a set F together with two binary operations called addition and multiplication. A binary operation on F is a mapping from the Cartesian product of F with itself to F. That is, a correspondence that associates with each ordered pair of elements of F. In other words, each pair from this set here, a uniquely determined element of F. The result of the addition of A and B is called the sum of A and B, and we write it this way. Keep in mind, this is more general than adding numbers. We can have, for example, matrices or complex numbers or functions. So this is a very general term for addition here. Same thing for multiplication. We write that as A dot B. These two operations, addition and multiplication, are required to satisfy these properties for a field. As we'll see, it's almost the same as a ring, but there's two additions. So associativity of addition and multiplication. So that's the same for rings. Then commutativity of addition and multiplication. So the multiplicative commutativity is something in addition that we have for fields but not rings. So that's the first difference. There's a second difference, which I'll get to in a minute. Additive and multiplicative identity. So A plus 0 for any element in our field is equal to A. So this is the additive identity. Then we have the multiplicative identity, A times 1 equals A. And it's also true that 0 plus A equals A and 1 times A equals A. That's because we have commutativity of multiplication, so we don't need to write it out. Additive inverses. So for every element A, there's an additive inverse. Then multiplicative inverses, that's something we don't require for rings. So for every non-zero element in F, there's a multiplicative inverse, written this way or this way, such that when you multiply A times A inverse, you get 1, or because of commutativity, if you multiply A inverse times A, you also get 1. Then we have the distributive law, written here. And you notice we only needed to do it on the left. Because of the commutativity property, we also have B plus C times A equals something similar to this because of commutativity. So we don't need to write it twice. But in the case of rings, if you recall, we had two versions of distributive multiplication over addition because of it wasn't necessarily commutative with respect to multiplication. We have two shorter definitions of a field. These both come from the Wikipedia article. An equivalent and more succinct definition is a field has two commutative operations called addition and multiplication. It is a group under addition with 0 as the additive identity. The non-zero elements form a group under multiplication with 1 as the multiplicative identity. And multiplication distributes over addition. We notice that saying that the operations are commutative implies this group, the additive group, and the multiplicative group are both commutative. Then we have an even shorter definition. A field is a commutative ring where 0 doesn't equal 1, and all non-zero elements are invertible under multiplication. So that's really to the point. It's just highlighting the two differences between a field and a ring, the commutativity under multiplication, and then having multiplicative inverses. In terms of notation, we sometimes write AB instead of A dot B. And then we have this other entity called a division ring. If multiplicative commutativity is dropped while keeping the other field axioms, the structure is instead called a division ring. Examples. An example includes the quaternions, represented by this H here, where multiplication is non-commutative. The quaternions are sort of a four-dimensional extension of the complex numbers. I'll give you a reference. This will be to the Wikipedia article. And then, on the other hand, finite fields like f sub p and real numbers are commutative fields. F sub p is the integers mod p, where p is a prime number. I've talked about those in a previous lesson. The following theorem relates rings and ideals to fields. A non-zero commutative ring R with multiplicative identity 1 is a field if and only if its only ideals are 0 and the ring itself. Assume that R is a field with a multiplicative identity 1. Take any ideal in R. If that ideal is the set with 0 in it, then we're done. If I does not equal the set with 0 in other words, it contains some non-zero element, and every non-zero element in a field is a unit, then it follows from theorem 22 that I, our ideal, equals all of the ring R. That comes from theorem 22. And just a note here, I could just say ideal or two-sided ideal here because we were given that R is a commutative ring. And I want to point out that the non-zero condition here applies going in both directions to the ring. So going in the other way, assume that the only ideals of R, ring R, are the set with 0 and the ring itself. Since we're given that R is non-zero, it contains an element A not equal to 0. The principal ideal A must equal R. Since we assume the only ideals of R are 0 and the ring itself, and A doesn't equal 0. Since R equals the ideal generated by A, there exists some small r in our ring such that 1, the multiplicative identity, equals R times A, which implies that A, which we picked arbitrarily, has an inverse, and thus R is a field. The rational numbers, Q, the real numbers R, and the complex numbers C, are examples of fields with an infinite number of elements. For any prime number P, the integers modulo P form a finite field of order P, denoted F sub P, or GFP, where GF stands for Galois field. These are the simplest finite fields. In F sub P, addition and multiplication are done modulo P. The additive identity is 0. The multiplicative identity is 1. This is 0 mod P and 1 mod P. The additive inverse of A is P minus A. The multiplicative inverse of a non-zero element, A, can be found using the extended Euclidean algorithm. Since P is prime, then the GCD of A and P is just equal to 1. So I give a few examples here where N, or P I should say, is 5. And so you have these 5 elements. Then here's an example of addition. 2 plus 4 is 6, but mod 5, that's 1. 2 times 3 is 6, again, that's 1 mod 5. So the multiplicative inverse of 2 is 3, and vice versa. 4 times 4 is 16, that equals 1, so the multiplicative inverse of 4 is 4. And of course, the multiplicative inverse of 1 is 1. So we've basically established that we have multiplicative inverses for all the non-zero elements. A field homomorphism is a function phi between two fields f and k, such that for all a and b and f, we have the following three properties. Phi of a plus b equals phi of a plus phi of b. Phi of a times b equals phi of a times phi of b. And the multiplicative identity of f gets mapped to the multiplicative identity of k. A field isomorphism is a bijective homomorphism, so it satisfies these three properties. It's a one-to-one mapping between f to k, and it's also onto. So for every element of k, there's an element of f that gets mapped to it. That's what onto means. If an isomorphism exists between two fields, f and k, they are said to be isomorphic, and we denote that by f isomorphic to k. This means they are structurally identical as fields. Then we have a crucial point here. The definition of a field isomorphism is fundamentally about the preservation of both field operations, addition and multiplication. It is a necessary consequence that such a map is also an isomorphism of the underlying additive and multiplicative groups. However, this group-level isomorphism is a byproduct, not the defining property. One cannot define a field isomorphism solely by the condition that the additive and multiplicative groups are isomorphic. And then we have a definition here. Finite fields are also called Galois fields, or fields with a finite number of elements. And we have an associated theorem. The order of a finite field, in other words, its number of elements, is either a prime number or a prime power. For every prime number p and every positive integer k, there exists fields of order p to the k, all of which are isomorphic. And for proof, I'll refer you to the Wikipedia article, Finite Fields, and the section is Existence and Uniqueness. I'll put a link to this in the information to this video. As I noted on the previous slide, finite fields are either a prime order, isomorphic to the integers mod p, so we know how to construct those, or of prime order p to the n. On this slide, we'll describe how to construct fields of prime power order. So given a prime power, q equals p to the n, where n is greater than 1, the field f of fq, in other words, this p to the n, also written Galois field q, may be constructed as follows. And I'll give you two examples of this. It's a bit of a long procedure to do even one of these, so let me first give you the procedure here. So the first step is choose an irreducible polynomial px in fp of x of degree n. Such an irreducible polynomial always exists. By irreducible polynomial, we mean a polynomial that cannot be factored into the product of two non-constant polynomials in f sub p of x. So we find that first. Then construct a quotient ring, fp of x slash p of x. The quotient ring is the field of order q that we seek. So in other words, f sub q is isomorphic to this quotient ring. P of x, the ideal generated by P of x is an ideal consisting of multiples of P of x, i.e. it's this set here, f of x times P of x, where f of x is in the field f sub p. P of x is the additive zero of f sub p of x slash p of x. In other words, it's the zero of this quotient ring, since the remainder when dividing by p of x by itself is 0. All multiples of p of x are in the same equivalence class as p of x. Elements of the quotient ring are of the form f of x times p of x plus a remainder, where r of x, f of x is in our field f sub p of x, and the degree of r of x is strictly less than the degree of p of x, which equals n. So basically we're looking at the remainder being polynomials of degree n minus 1 or less. And that's how we go about finding all the elements in this quotient ring. So this will become a little clearer, hopefully, with an example. I have a few more comments here concerning our algorithm mentioned from the previous slide. The elements of f of q are polynomials of fp of x whose degree is strictly less than n. I said that at the end of the last slide. Addition and subtraction in f sub q, which is, if you recall, that's a quotient ring, is defined by addition and subtraction of polynomials in f sub p of x. Multiplication of two elements in f sub q entails the product of two elements and then taking the remainder upon long division by p of x. So everything is mod p of x in this quotient ring. The multiplicative inverse of a non-zero element may be computed with the extended Euclidean algorithm. So this is the, from the last slide and this slide, this is the explanation of the way that we find our f sub q finite field where q is a power of p. And now I'm going to give you two examples in the remainder of this lesson. As our first example, we're going to construct f4, so the finite field with 4 elements with respect to the above procedure we just talked about. So in this case, we have q equals 2 squared. So our n is 2 in this case. In f2 of x, there's only one irreducible polynomial of degree 2, and that's x squared plus x plus 1. In f2, the integers mod 2, we only have two elements, 0 and 1. And so p of 0 is 1. And p of 1, you get 1 plus 1 plus 1, that's 3. But 3 mod 2 is 1, so that's 1. Thus, p of x is irreducible. To prove p of x equals x squared plus x plus 1 is the only irreducible polynomial in f2 of x, we can do it by exhaustion since there's only 8 possibilities. If we take the general form here of second degree polynomial in f2, then a is 0, 1, b is 0, 1, and c is 0, 1. And then we can just test each one, and you'll see that this is the only one that's irreducible. Next, we determine the elements in our quotient ring. So it would be f sub 2 of x mod the irreducible polynomial, each of which is a remainder of the polynomial f sub 2 when divided by our irreducible polynomial. This means the elements of our quotient ring are of the form ax plus b, where a and b are in f2, the integers mod 2. And since a and b are either 0 or 1, there are only 4 possibilities. So our task is not that hard since we only have 4 cases here. So to complete our example, we want to find the addition and multiplication tables for the 4 elements in our group represented by this quotient ring. So we need to look at the cosets. The first one is 0 plus the irreducible polynomial, which is the identity, the additive identity. And then there's 1 plus this irreducible polynomial, and that's the this is the remainder when you divide by this. So you get another element, another coset, and that's the multiplicative identity. And then you get 2 more. You get x and x plus 1. So the 4 elements are 0, 1, x, and x plus 1. Remember, it was everything of the form ax plus b, and there's only 2 possibilities for a and b. For some reason, what I've seen in different books, online articles, they seem to want to assign the Greek letter alpha to x. So I'll go ahead and do that. So basically we have 0, 1, alpha, and alpha plus 1 is our 4 elements of f4. And then I have the addition table here for each element. So of course, 0 plus anything is 0. So this row and this column are pretty easy. Then 1 plus 1 is 2, but 2 mod 2 is 0, so that's not too hard. Then 1 plus a gives you another element, 1 plus a. We don't need to do any reduction there. 1 plus a. And then 1 plus 1 plus a. The 1 plus 1 is 2, so that cancels out, and you just get a here. Then you would get the same things going down this way, right? This is a commutative group. And alpha plus alpha is x is 2 alpha, but 2 is 0, so you get 0 here. And alpha plus 1 plus alpha, again, you get 1 plus 2 alpha, but the 2 is 0, so you just get 1. Same thing here. Then the last one is, I actually wrote it out down here. You got 1 plus alpha, 1 plus alpha, but that's 2 plus 2 alpha, so both of these are 0, and you just get the 0 here. Okay, so that's the addition table. I'll do the multiplication table on the next slide. So we want to look at all the possible ways of multiplying 0, 1, alpha, and 1 plus alpha times each element of the group. So a lot of this is easy. 0 times each of these is 0, and each one of these elements times 0 is 0. So this row and this column are pretty easy. And then 1 is also easy. 1 times each one of these is just the element itself, and each of these elements times 1 is the element itself. So we're just left with these 4 in here that take a little bit of thinking. So I've done some explanation up top here. We need one other fact to compute the multiplicative group beyond what I've just discussed. So since x squared plus x plus 1 is the 0 element, we have x squared equals minus x minus 1, but minus 1 is just 1 modulo 2, so you just get x squared equals x plus 1. So keep that in mind. We'll need that when I'll go through it right here. When you multiply alpha times alpha, which we've substituted in for x, again, I don't know why books are doing that, but I'm just following the convention. You get alpha squared, and that's alpha plus 1, so you get that in here. And so what else do we have? We have alpha times 1 plus alpha, so that gives you alpha plus alpha squared, and that's just 1, using similar logic to what we've done here. Then it's the same thing here. And then finally, and I've written this one out, if you take 1 plus alpha plus 1 plus alpha, you get 1 plus 2 alpha plus alpha squared, but the 2 is 0, so you just get 1 plus alpha squared. And that's the same as 1 plus alpha. That's what we computed up here. So that gives you 2 plus alpha, and then that's just alpha. So we get what I'm showing in here. For our second example, we're going to construct F8, so the finite group with 8 elements. In this case, we have Q equals 2 cubed, and so n equals 3. In f sub 2 of x, there are several irreducible polynomials of degree 3. P of x equals x cubed minus x minus 1, and x cubed plus x squared plus 1. So we can use either one. We will use this first one here, P of x, in the following calculations. So we want to determine the quotient group f2 of x slash x cubed minus x minus 1. So the elements of this quotient ring, will make up our F8. The elements of this quotient ring are of the form ax squared plus bx plus c. So we're basically the remainder is of degree less than the irreducible polynomial, so it will be a degree 2 or less. So in this case, we have A, B, and C in F2, and so there's 2 times 2 times 2. There's 8 possible, 8 not possible, but 8 elements in F8, which matches up with our expectations. Again, we'll let alpha equal x, and I may slip and say A sometimes. I noticed I did that before, so I mean alpha, but we have this here. So the possible elements of our F8 are 0, 1, alpha, alpha plus 1, alpha squared plus 1, alpha squared plus alpha, and alpha squared plus alpha plus 1. This one here is a case where A, B, and C are 1. I'm just taking different combinations of A, B, and C being either 0 or 1, and that'll give us our 8 elements. So our task from here is to do the addition table, so it's be an 8 by 8 table, and then the multiplication table for these elements, and then we'll have constructed our F8. On this slide, I have the addition table for F8. Let's just look at a few of them. Most of them are pretty straightforward. Let's look at the ones in green. So if we have alpha plus 1 plus alpha squared, we just get another element in our field. Alpha plus 1 and add it to alpha squared plus 1. We get alpha squared plus 2 alpha, alpha squared plus alpha plus 2, but 2 is 0 in the integers mod 2, so that's alpha squared plus alpha. Then alpha plus 1 added to this, we're going to get alpha squared plus 2 alpha, but the 2 is 0 in our F2, and then plus 1, so we just get alpha squared plus 1, and then one more alpha plus 1 added to this, and you get alpha squared, then 2 alpha plus 2, but the 2 alpha and the 2 are both 0, so you just get alpha squared. Notice that the thing in gray here, this part of the table, is actually F4, the addition table for F4. Maybe one other point, whenever you add elements where the coefficients are coming from F2, you're always going to get 0. So you notice you have 0 down the main diagonal because you're adding things of the coefficients that are 1. So for example, this one here, added to this, you're going to get 2 alpha squared plus 2 alpha plus 2, but all those are, each coefficient is 0, and you just get 0. Okay, let's now look at the multiplication table. That's a little bit more complicated. So we need some preliminaries before we can do the multiplication table, and I went through those preliminaries on this slide. So since x cubed minus x minus 1 is the 0 element, we have x cubed equals x plus 1. We'll use that to simplify some of the multiplications. So within the quotient ring, again, we're using alpha in place of x. We get alpha cubed equals alpha plus 1. And with this information, we can compute the powers of a, higher 3 and above, I should say. So we get alpha cubed equals alpha plus 1. So we already established that. Then alpha to the 4th is alpha cubed times alpha. And then we can plug in this for alpha cubed, and we get this here. And that gives us alpha squared plus alpha. And that's one of our elements from F8, so we don't need to do anything there. Then we go to the next one. We can write alpha to the 5th is alpha to the 4th times alpha. We just plug this in for alpha to the 4th. And then we get alpha cubed plus alpha squared. And then we know alpha cubed is alpha plus 1. And we get another element from our F8. So we want to stop when we get an element from F8. So this is not an F8. That's why we did another step here. Then alpha to the 6th is alpha cubed times alpha cubed, which is alpha plus 1 squared. We get this here, but the 2 is, of course, 0 on F2, which I mentioned here. And so we get alpha squared plus 2, alpha squared plus 1. Then alpha to the 7th is alpha cubed times alpha to the 4th. We just plug in these two here. We get this. The 2 is 0. Then we just get alpha cubed plus alpha. And alpha cubed is alpha plus 1. Then we add those together. And the 2 alpha is 0. And then we just get 1. So the powers of alpha generate all of F8. In other words, it's F8 is a cyclic group with respect to multiplication. This is just a comment, not necessarily related to what we want to do here with the computing the table. So on the next slide, I'll show you the table. I won't go through every last one of the computations. You need to use these identities here in order to complete the table. I'll just go through a few examples. On this slide, I have the multiplication table for F8, the finite field of order 8. And I also put the computations that we did on the previous slide down here for our reference. I checked this with the LLM DeepSeek. I provided the table and it checked it row by row, and it confirmed that these were all correct. You may want to check some just for your own benefit, just to make sure you understand this. I'll just do the ones in green here, just to give you a feel for it. So alpha squared times alpha squared is alpha to the 4th. And as we compute it, that's alpha squared plus alpha. Then alpha squared times alpha squared plus 1 is alpha to the 4th plus alpha squared. So it's this plus alpha squared, but that gives you 2 alpha squared plus alpha, and the 2 is just 0. So you just get alpha. Let's look at the next one. You get alpha to the squared times alpha squared plus alpha. That'll give us alpha to the 4th plus alpha cubed. So if you add these two together, you get alpha squared. 2 alpha is 0 plus 1, so that checks out. And then alpha squared plus this here, and you get, or times, excuse me, alpha squared times alpha squared plus alpha plus 1. So you get alpha to the 4th plus alpha cubed plus alpha squared. So you get these two added together, plus alpha squared. So the 2 alphas cancel, and then you get, and when you add alpha squared to the alpha squared here, that's going to give you 2 alpha squared, so that cancels to 0 again, so you just get 1. So that checks out. Okay, so I'll leave the other ones to you if you wish to check them, but as I say, I double checked it with artificial intelligence, and they all come out correct. All right, we're almost done. We have one more slide in this lecture. What we saw for F8 in our previous example, where we had alpha generating the entire field of F8, is a part of, or a consequence of a more general theorem, which I'm listing here. I'm not going to prove it, but I'll give you a reference to where you can find the proof. So let's look at this. It says the multiplicative group of all non-zero elements of a finite field is cyclic. So that's a powerful theorem that gives us a fairly good characterization of all the finite fields. Okay, so that's it for this lesson, and that's the only lesson I have on fields. I'm going to do one more lesson in this abstract algebra playlist, and that'll cover vector spaces, fairly high level, and also something called algebras, and then that'll be it. That'll be the last lesson in this playlist.